I probably will turn my video off because sometimes my internet is not fast enough. So in order to make sure my voice is clear, I'll just turn off the video. And if you have questions, you can post on chat, or you can maybe just speak up. So it's my pleasure today here to share with you some of our work on improving GISS model simulation of the particle number concentration. So this work we carried out in the last couple of months. And first, I would like to acknowledge Gan Luo and Xu Ne in my group. Gan spent a lot of time to run the GISS model, and Xu is a graduate student here. He worked on the machine learning algorithms. And I think both of them are here. So if you guys have questions about a specifics, they can also probably help to answer. And I also wanted to thank Costas and Suzanne in the past several weeks, or even earlier, several months. We have email exchange and discussions, and they definitely help us to understand more about the GISS ModelE. Actually, this work, part of this work, we have a manuscript and we have a complete manuscript, so we kind of try to revise and finalize that. So that's the information we have right now. How to move? Okay, so I think everyone here know aerosol have direct and indirect climate impacts, and it's very clear direct is related to the scattering absorption of the solar radiation by aerosols. And aerosol also affect cloud and precipitation by acting as the cloud droplet number concentration. So these have large uncertainty, and it's a lot of ongoing research. What this ship track is just one clear example how aerosol may affect cloud albedo. We call the first indirect effect. So if the liquid water content is same, if you get more aerosol, you get a small droplet, which will change the cloud albedo. And that's something we try to focus on in this study. And these droplet number concentrations, we call it cloud droplet number concentration, depend on aerosol number. And that's why we want to study aerosol number, as I will illustrate in more detail later. So GISS model, in this study, we focus on GISS model. I think most of you know GISS climate modeling has a long history, dating back to 1970s. And has been involved in a bunch of CMIP model comparisons and import. So this model is important and will be continued to make a significant contribution to CMIP. 3 versions of the GISS E2.1 simulation have been submitted to most recent CMIP 6. One based on non-interactive aerosol simulations. It's offline. The second simulation is use the one-moment aerosol model. We call it OMA, which is mass-based aerosol schemes. And there's another one, MATRIX. It's based on a kind of mode method, give you a size distribution of different aerosol types. One interesting thing, and as reported in a recent publications by Suzanne et al., the values, so aerosol radiative forcing, the value and the trend is quite different based on the MATRIX and OMA. So what is shown here is aerosol direct forcing. So red one is the MATRIX, and this blue one is the OMA. You see kind of different trend. If you look at the something here, if you look at the CD and C, you also see different MATRIX and OMA, quite a significant difference. If you look at the aerosol indirect force or cloud forcing, the value is differ by 0.4 to 0.5 watt per square meter, and also have kind of different kind of trend. So these are interesting, and we try to understand why. I think the different reasons could cause this difference, and one of them definitely is the aerosol. So in this study, we try to look into the aerosol. So back to the aerosol, how important aerosol. Aerosol indirect effect largely depend on the cloud droplet number concentration. So in order to affect the cloud aerosol will change the cloud droplet. So these CDN, we call it CDNC, depend on the particle number concentrations. And that have been observed in a lot of airborne field campaign. So if you fly the aircraft, you go to the cloud base, measure the aerosol number concentrations, and you fly it into the cloud and measure the cloud droplet number concentration. You see this kind of the dependence. More aerosol number, generally you get more cloud droplet number concentration, which is, I think, physically makes sense. Of course, depending on different locations, the sensitivity is different. So in order to get the aerosol effect on chloride, aerosol number is important. However, the particle number concentration calculations are generally simplified in Coupled models. I think there are two reasons. One is computing cost. So if you wanted to get the aerosol number, you need a lot of the size resolved aerosol microphysics, which is computing cost. So for Coupled models, that's just probably too expensive. Another thing is a challenge in including the size resolved particle microphysics. So if you wanted to get the number, you need the size resolved microphysics. That's also a challenge. So if we look the CMIP6 model, it's most recent model for the climate simulations. So this is a paper published by Zenith et al. In ACP. They compare 10 CMIP6 climate models. 7 of these models employ bulk mass-based aerosol scheme. So only simulate the mass, not the number. So these models use mode or moment aerosol schemes. So it's still quite simplified. So the objective of this study, we try to use machine learning and also up-to-date aerosol schemes to improve GISS ModelE simulation of particle number concentration, and use the model to study implication for indirect radiative forcing. By the way, the GISS model also involved here. So you see the co-author, Costas and Suzanne and other people. Here's the outlines. So I will describe kind of briefly in 5 aspects of this study. First, we look at GISS and we improve the SO2 and the self mass concentration model simulation based on GISS ModelE 2.1. We also, in the second part of talk, I will describe, we use machine learning to improve the OMA simulation of PNC, so mass-based schemes. We also talk about updates to improve MATRIX simulation of particle number concentration. So it's all related to particle number concentration. Then we use the GISS OMA after the improvement. We see how that may affect the aerosol indirect cloud forcing. And then in the end, I will talk about what's the possible further application use the machine learning to improve the GISS ModelE. So I will have some time to discuss that. So let's move to the first part. We know SO2 is an important precursor for both OMA and MATRIX model. So this improvement actually is based on our experience with updates to relevant process in GeoScan. So we published 2 papers in GMD just last year and this year. And we're looking a number of processes, including the aqueous chemistry, dry depositions, wet scavenging process. And based on that experience, we update relevant process in GISS. And we will show that's improved SO2 and surface simulations. I probably do not have time getting into detail about the improvement. These are described in the paper, the draft paper we have right now. If you are interested, you feel to contact me or maybe Costas. So just quickly, we updated aqueous phase chemistry based on scheme we have. We also, I think one thing we consider the ozones, oxidations of sulfur by ozones. We also consider the solution of aqueous phase reactive gas in cloud. So these are the processes, some update. We also consider the change in the rain out and wash out, use the harness law coefficients. So we update the schemes to calculate the dissolutions of these gas in rain cloud, in rain out for rain out and wash out. For the aerosol, we also update the aerosol rain out efficiency. So there are different schemes and they are reference, and we just updated to the recent publications we have. In the convective cloud, we also updated the condensation scavenge. And for washout for aerosol, we updated the scheme of the dilute or use some more empirical washout rate as reported in our recent paper. For SO2 evaporation in cloud water and lake water, we also updated the schemes. For the dry depositions, we also have the update for both aerosol and for the gas, especially over cold area, over snow and ice. We updated the dry depositions, mainly SO2. And we will see these have a significant impact on SO2. So again, these are pre-belief. If you need a detail, you can contact me or Costas or maybe Suzanne. We have paper describes that. So I just want to summarize these updates changes the SO2 simulations and the surface. Mostly here I show the SO2 because again, SO2 is a precursor important for the aerosol formations and also the aerosol surface mass as well. So what is shown here is the SO2 concentrations over US, Europe, and East Asia compared with some network measurement and also survey. What you can see here is there are several lines. Black one is observations. It's a multi-site average. Original one is in blue, and red one is in kind of updated one. So it's based on our update. So what you can see is in the summer, like in the Europe, there are not much difference. But in the cold seasons, you'll see the significant improvement in the SO2. Original model kind of almost estimate as SO2 in the cold seasons. And again, that's based on the GISS ModelE 2.1. I know GISS have E3 ongoing, so maybe some of scheme already updated there, but this is based on E 2.1. For the Asia, we kind of model still overestimate, but the measurement side is more only 3 sides. For the US, there are 2 sets of the observation. One is more urban, another more rural. We are kind of in between. It's a global model, 2 by 2.5. But again, we will see the improvement in the winter seasons, so getting more close to the observations. For the survey, not much change, but generally kind of improve a little bit. For the, I think the most improvement, and when we evaluate the GISS model, we find overestimated, and that's lead to overestimate of the particle numbers concentration in MATRIX, as we will see later. So after we consider the update, we're getting more closer to the observations. We also compare with atom. So you look at the vertical profile. The original, you see the SO2 is overestimated in the middle and upper troposphere, especially in the remote region. So atom is in over the remote oceans. After we updated these calculations, SO2 is getting closer to the observations. So these are the update. And we make this update because we know SO2 is important for new particle formations. We want to make sure that's in the reasonable range when we consider the particle number concentration or new particle formations. So now I will move to use of machine learning to improve particle number concentration simulation in OMA. In GISS OMA, and that's a mass-based aerosol scheme, it's supposed to simulate the aerosol mass, not the number. However, if we wanted to study the aerosol impact on cloud, we have to simplify. We have to get a cloud droplet number, because that's the only way you consider the effect of aerosol on cloud. So in the GISS OMA, the scheme used to consider the aerosol impact on cloud has been derived in Menon and Lotztan in 2006. So basically, there are 2 sets of the parameterization. One is from particle mass to particle number, assume certain kind of size distributions. So basically, you get a mass to number conversions for different mass of the different component. So particle number concentration is a function of this mass. After you get a particle number, there are another of parameterizations connect the aerosol number to the cloud droplet number. So when particle mass change will change the particle number, then particle number change will change the cloud droplet number. So in this study, we don't change this, keep this same, but update the scheme for this. We see if we can improve this, because this is only based on the mass only. And we try to see if we can use the machine learning to get the number more accurately without induce a lot of computing cost. So again, particle number calculations are so we try to use a global size resolved model and a machine learning to solve this kind of physics to imply in the schemes use the machine learning. So it's computationally efficient, still good for the climate model, and also it's easier to use. So you don't need to worry about how you deal with the size resolved microphysics. how you to assume certain things. So I think that some of you probably know the machine learning. Machine learning actually is a subset of AI. And of course, AI, machine learning also have deep learning, but we first focus on machine learning. The idea of machine learning use the computing algorithm, try to let the machine or compute to learn things that we don't tell them to learn, but they figure out. Okay, that's I think the simple word. In order to get the machine learning, we need a large amount of data to train the machines. So you give the machine a lot of the situation, a lot of data, and the machine have the algorithm to try to figure out things. For this study, because ideally we want to have a lot of observations, but for aerosol number and measurement is quite limited. So we use outputs from a global size resolved particle microphysics model. We call it GISS APM to train the machines. Of course, this model is important. We use the model output to train the machine. So the performance of model is important. So I will spend a little bit to discover this model. This GISS model with size resolved, we call it advanced particle microphysics model, have been developed and used in the past decades. They consider very detailed, full size resolved beam microphysics. So we have 40 beams for second particles, 15 beams for black carbon, 15 beams for primary organic carbon, 20 beams for sea salt, 15 beams for dust. Okay, so it's a beam model with different number of beams for different type of particles. We consider the coating of primary particle, like the primary black carbon, if they get coated by the second species due to condensation or coagulations, we keep track of that because this coating is important for their optical properties and also their ability to act as the cloud condensation nuclei. In this scheme, we consider all detailed microphysics, starting from new particle formations. So new particle formation can involve sulfur acid, ions, amine, ammonia, or even organics. So we have a lot of study use the GISS APM to consider kind of state-of-art nucleation schemes. We consider the growth of these particles explicitly by the condensation of sulfur acid, uptake of ammonia and nitrate, and also the condensation of low, sometimes called extreme low volatile second organic gas, and also partitions uptake of the semi-volatile or medium volatile second organic gas, which is coming from the VOC oxidation. And these particles can grow, and then when they to the CCN size, they can interact with the cloud. So these are the detailed process in GISS CAM. And we learned this GISS CAM for the past 30 years at the 2x2.5. And this output, very detailed output, we used for machine learning. Again, we wanted to make sure this model simulation is reasonable. So we compare with some observations, and we publish a number of papers. Here, I just give you several examples. What's shown here is because this is size resolved model, we can simulate the particle size distributions at any grid box, any times in the globe. So here, just give you one example of the Pinnacle State Park. We have a site, ASRC, Albany, have a site there. It's a remote regions. And what's shown here is the model simulate particle number size distributions during the last 19 years. You'll see the change in the particle size distributions. And if we zoom in to the 2 period about 2 weeks, which we have the measurement. So here is the particle size distribution measurement. And this is the model simulations. So what is shown here, the Y is the size of the particle, and x-axis is the time. And the color shows the number concentration, is dn d log dp. So you can see the model captures this kind of new particle formation and glow events quite well. Miss or maybe over predicted in some place, but most of the place looks pretty good. And we compare with other side as well. Model generally capture the new particle formation and growth. And you can see these new particle formation, and they can grow to a CCN within a day, and they dominate the particle number. So we are talking about the particle number. These numbers are dominated by new particle formations. If we want to get the particle number right, we need to get this process right. And we compare with a number. There are more number measurement. So that's the last 18 years. And during recent years, we have the particle number measurement. And if we zoom in during the last 4 or 5 years, the model actually captures this kind of seasonal variation and even daily variation, like here. So give us the confidence about the model ability to get the number right. And if we have the number right, then we can use the output to train the machines. We did another study, compare with airborne measurement from the Discover AQ over the DC area. Okay, airborne, you can have aircraft measure in the kind of the above the surface. So during that July month, actually in the summer, you see the aircraft. So our aircraft go up and down, but you see the new particle formations even in the summer. So sometimes you get even pretty strong. So it's in top of mountain layer, about 1 kilometer or 2 kilometers above the surface. You see the new particle formation. Again, this new particle formation dominate the particle number, and they can grow to the CCN. And this is the model simulations over these regions. Model you see capture these kind of nucleation events, not every day, but certain days. You see the new particle formation. If we zoom in, we get a model of the particle from previous day, but the new particle formation and growth. So these particle formation also contribute to the CCN. And this 3 panel just the surface measurement. So near the surface, you also have the measurement. So indicate in the summer, particle also form, they can grow. And CCN process. So these are the 2 examples we show GISS APM can capture this process. Now we come to the machine learning. Okay, so what that means? Machine learning have different kind of the method. What we use is we use a random forest regression model. Okay, so quickly, what does that mean? Means we select a bunch of the input variable, and we select based on the information or variable available in bulk or mass-based error scheme. That's a GISS model. Actually, this selection is based on both GISS and GISS-Chem. GISS-Chem have similar kind of aerosol species with GISS. So we select the PM species. So these are the common mass. So that's all available in the model. In addition to that, we also consider trace gas, SO2, NOx, and all these species are available in GISS model. We also consider the meteorology information, temperature, relative media pressure. And we have all these information as an input variable. And of course, the GISS-Chem also predict the particle number concentration. Okay, so what we use is we put that in the machine, and machine try to figure out what's the particle number concentrations. So how they do is we use the random forest What that means, we have different number of trees. It's called decision trees. And these trees will decide, based on this, we have 18 variables. And based on all these 18 variables can predict the particle number concentration under that condition. But we have n, in this case, sometimes we get 130 trees. And all these trees give you a different number of the particle number concentration. And this is like an sample idea. And we average that to get the particle number concentration is what its output. So these schemes, we have been used for the CCN, and the detail of this scheme have been described in a paper which just appeared, I think, in ACP today, or maybe if not yet, tomorrow. Final version of the paper will appear there. So for the particle number concentration, we compare this random forest with the GISS CAM. So this number, we save a set of the data that's not used for training. So it's independent. Then we use these schemes to compare. So generally for number, we get a high correlation of 0.77 with median mean fractions is it's pretty close on average. And the percent of agreement is also pretty decent for particle number. Actually, for CCN, performance is better, and I will show a little bit later on. So we can use also use
sorry to interrupt. Hello? We actually have a question about this point in the chat that Allegra raised. Okay. Allegra, do you want to unmute yourself and ask?
Yeah, go ahead and ask. That's fine. Yeah.
Sure. So those correlation and bias numbers, can you put those in context of some more traditional regression techniques?
You mean the correlation?
I mean, for instance, if instead of using the random forest to regress those 14 input parameters against the outputs, what if you use like a linear regression or some other types of regressions?
It's not a linear regression.
I know. That's what I want to know. I want to know the context. So is a correlation of 0.77, is that really good or significantly better than non-machine learning or equivocal?
Yeah, that's a good point. We did some study, analyze that, compare the random forest and with just the simple multiple variable regressions. And the random forest definitely is better than that. It's improving. So it's not a linear regression or even multiple linear regression. It's based on the decisions. So basically split a lot of the if and the if. So they want to try to find all the similar situations. So it's a different idea based on my understanding. And Arshid probably can jump in at some point or maybe late. We compare with multiple linear regressions, and the random forest it's better than that. I probably do not have time to look into that. In the paper, we're probably working on paper try to demonstrate that. But this performance is better than the regressions. And I think the bias and also the agreement, we use kind of 60% within that range as a judgment. But I think that it's no definite point what is better, what is not good. But that's the way to measure how good is that. Okay.
Thanks.
So I hope it answers your questions. We found it's quite a challenge to calculate the particle number concentration. For the CCN actual aerosol extinction coefficient, the agreement is much better because they probably dominated by large particles. And I will show a little bit later on. Okay, so then we apply that to the GISS OMA and try to see how that affects things. Okay, So what we shown here is particle number concentrations simulated based on OMA, based on simple mass to number conversion efficiency coefficients as used in the model. And that's the simulations. And we compare with these other side, we find the annual mean particle number concentration data. This is used in machine learning. So we add this scheme in the OMA model, and the computing cost is increasing by 5%, roughly around 5%. And if we compare with observation, because you see the difference, but how much it improved, we have to compare with the measurement. Actually, if you look at this side, the OMA agreement is not that bad. The correlation is 0.82, linear correlations. But machine learning improved correlation, not that much. I think that's mostly because it's a spatial variation dominated by the emissions. But we do see in some site, remote site, you see some deviations. So normalize the mean bias also kind of improved, use that. But I think another things we find for the time series, so this is the average value. If you look at the time series, we select the site in Pinnacle State Park, it's all here. So these locations, if you look here, all is both scheme actually give pretty good annual mean particle number concentration at this site. But if you look at time series, you see quite different. Okay, so observations, particle number concentration observed at this site. Blue one is the OMA, and the green was the machine learning. You see quite a substantial improvement in the correlation coefficients. In the summer, OMA over predict, but the machine learning able to capture that. So I think that's encouraging. And in order to study aerosol impact on cloud, we not only the kind of spatial variation, the time variation is also important. So that's for the OMA. And I will show some, next I will talk about some of the updates we made to improve the MATRIX simulation of particle number concentrations. So I think you know MATRIX is another aerosol model in Model E. It's a mode or moment-based aerosol schemes, have the aerosol microphysics and have a size information. You can consider different number of aerosol populations and size distribution. Activations. Use the aerosol activation parameterization. One thing we noticed in this paper published last year is the model kind of intercomparison for particle number and CCM number. And this study indicates that MATRIX significantly overestimate the particle number concentration. And these are the figure, particle bigger than 3 nanometer. These are the all the models. I think the 15 model median. You see the number concentrations, and that's the matrix. You can see first. I want to part of the scale is different. Here is you get 1 source, and here you get 60 source. So you see the color scale different. And even in this color scale, you see very, very large particle number concentration in the matrix. And if you compare with observation, it's way too high. And of course, particle number is important. So we wanted to understand what the possible reasoning. Of course, the reasoning can be two. One is the nucleation scheme or new particle formation scheme used. So actually in the matrix, there are several nucleation parameterization can be used. One is a ternary homogeneous nucleation of Napoli et al., and that's used in this intercomparison paper. Another is binary nucleations, Karmaki et al., 2002, and that's used in CMIP 6 simulations. In the default setting, when we download the model E2.1, use binary homogeneous nucleation of this Karmaki1 and of Turco, and I developed quite a while ago. That's the default setting. So depending on which nucleation scheme you use, you probably give quite a different particle number concentrations. And of course, the particle number overestimation can be also caused by overestimation of the precursor gas. So I will show quickly. For the particle nucleation scheme, we actually just recently we developed we call it state of science nucleation scheme. Consider both the effect of ammonia and ions on nucleations, and actually both cloud in the laboratory measurement, and this model show the importance of ammonia and ions. So what is shown here is ammonia concentration impact on nucleation rate. So the symbol here is laboratory measurement. These are the TIMN, we call TIMN prediction. So we capture these kind of variations. This red line is just if you get more ions, you get more nucleations, which indicate ion is also important. The other line are other study, and I do not have time getting this point is for 2018. So we have implemented this scheme in GISS MATRIX. Okay. We also compare this scheme with other schemes commonly used in many models. So these TIM schemes we have implemented in the GISS MATRIX is the black one here. If you compare with Karmaki et al., and we compare with observation, Karmaki is often predicted by 4 to 5 order of magnitude. If you use Napoli et al., if you compare with the laboratory measurement, it's often predicted by 7 order of magnitude. So that's one of the reasons if you use that, you probably will only predict number concentration. So it's important to use the right nucleation schemes. Just quickly, we also find matrix often predicts the SO2 and the sulfur acid. So SO2 we already showed earlier, especially in remote regions. Sulfur acid we also update the schemes, and which we'll show in this slide. So this is the GISS model sulfur acid concentration. You can get up to 100 ppt in the polluted region. That's way too high compared to the measurement. And this is the updated one. And it's in the right range compared to the observations. Usually in the polluted region, you get a ppt or sub-ppt value. And if we compare the particle numbers, that's based on the default setting and just very high, even in the polluted region. So we also improve the metrics. So I probably, my time left is, I kind of run out a little bit of time. I'll be quickly go through these two parts. So we also studied the aerosol impact. So the purpose for us to improve particle number concentrations is to understand the impact on aerosol in direct cloud forcing. We know particle number is important because the particle number directly related to the cloud droplet number concentration. And we see the improvement. Then what's the impact on the cloud droplet number concentrations and aerosol indirect forcing? or effect radiative forcing due to aerosol cloud interactions. That's what we carry out use the OMA schemes. So that's the original OMA scheme. Okay, that's in the pre-industry and the present day emissions. And we learned the two cases based on current meteorology, but just change the emissions. You'll see based on original OMA, pre-industry global mean CDNC, cloud cover weighted CDNC, increasing by 61% due to the emissions. Of course, because there are a lot of natural aerosol precursors, so you all still have aerosol in pre-industry. It's increasing by 61%. If we use the OMA, use the machine learning in OMA, and we find that you get more aerosol, more CDNC in pre-industry, but less CDNC in the present day. And the increasing global mean is only by 28%. So you see the difference. And then we consider the effect radiative forcing due to aerosol cloud interaction and reduce from negative 1.46 to less to negative 1 in the effect radiative forcing. Okay, so I will quickly kind of discuss a little bit about what we can do, use machine learning to improve GISS ModelE. I think what we wanted to do is CCN. In the earlier, we should focus on particle number concentration. And based on our experience, CCN is more directly relevant for CDNC. So if we can derive CCN parameterization machine learning, if we have a scheme to connect CCN to CDNC, I think that will improve the reduce uncertainty. Actually, so CCN we find and we do quite some study to validate that on the work, and RSU is working on that. So what is shown here, we validated the CCN predicted by machine learning with the observations. So in this case, because observation, sometimes only you have 9 variables. Ammonium, nitrate, and the temperature, and also SO2. If we use these 9 variables to predict the CCN and compare with this observed, that's the time series. Actually, we see the machine learning capture this kind of variation. And in this case, quite a well agreement. So we are looking into that. For CCN, again, we show the agreement is better than the particle number concentrations. So we are kind of feel encouraged on that. And the CCN seems to do a better job as a model. And we also compare with other airborne. We are ongoing to analyze, use observe the CCN to validate the machine learning algorithms. Okay, and I will just skip this one. And we are ongoing research. We try to improve and validate the IFRM of machine learning algorithms. I think we probably can do a lot of things. We can also do the optical properties. So based on the machine learning to get the optical properties information, which is needed in OMA for the direct radiative forcing. And we can also, and I have some discussion with Costas and Suzanne a few weeks ago. We have a meeting and we discuss. We probably can also generate the size distribution information, so which you can use for explicit cloud activations, use the Stephen-Gang schemes. We probably can even go to get the cloud droplet number concentration machine learning schemes. So you get a CDNC from the machine learning algorithms, and of course, all these can be should be validated against the measurement. So that's, I think, a lot of can be started. I will skip this one. So quickly, and I probably just leave this here. And most of my point is in the abstract. So I'll just stop here, and if anyone have any questions, we can use the remaining time to discuss. Okay, thank you for your attention.
Great, thank you very much for the talk. Actually, there were a few questions that were just raised in the discussion. I'll hand it over to Gavin. Would you like to ask the question? I can also just read it from the chat, but if you want to unmute yourself. Okay, he wants me to read it. So Gavin wants to know, how do you prevent, how do you prevent or at the least assess the possibility of overfitting? Then there was some discussion that was had after that, but before we read that, maybe you can comment on that.
Okay, for this, I will refer to Arshid, my student. Arshid, are you there? Could you speak on that?
Yep. Am I unmuted?
Yeah, I can hear you.
Yeah, so in the use of random forests, overfitting of individual decision trees is corrected through multiple means. One is simply because you're taking an ensemble of a large number of trees. If they individually overfit, that will be smoothed out in the final product, which is basically your aggregation of each of those trees results. In addition to that, we use the mean fractional bias on a separate testing data set. So we keep a set of the GeoSchem APM data, which the random forest is not exposed to for testing it. And by using that, we can ensure that we don't overfit on the data. I hope that answers the question.
Great, thank you.
So we also discussed in the paper we just published in ACP, Ney and Yu. So we have some discussion there as well.
Great, thanks. Does anyone else have any other questions that they would like to ask? You can indicate so in the chat. Allegra?
Hi, thanks. So I did see you had present day versus pre-industrial comparisons, but did you look more at out of sample testing? Like if you push it, look at some RCP scenarios like end of century, or if you look specifically at just the volcano years and don't use that when you're doing your training. Are you able to capture how variability might happen in areas that are kind of at the extreme ends of your training period, or does it blow up, or how do you keep that from happening?
Okay, yeah, I think for the GeoSchem, it's consider the volcano emissions and all the possible kind of the scenario. We hope it's captured, but we will look into that. But we run the GeoSchem for 30 years with all the biomass burning emissions, volcano emissions, other emissions. And we hope the GeoSchem captures these kind of variations. I think one thing important is we feel, and we are looking into that, why is we can capture that. I think the machine learning kind of capture the relations between key precursors, like the SO2 emission from volcano. If we have that relations, if you get a high SO2, you get a high number of CCN, and that relation is captured. And if in the climate model, if you have the volcano emission, as long as you get more SO2, the model machine learning algorithms able to get this kind of relations. Even the GeoSchem may not have that particular emission in the model, but if you have the relations, I think the machine learning algorithm able to capture that.
Great. We have another question. This is from Ron Miller. Ron, do you want to unmute yourself?
Hi. Yeah, this is related to the question that Gavin and Allegra asked, just about robustness. So with the current version of OMA, as you point out, you get sulfate number, we basically have to know the sulfate mass, and that's the only relation we need. So with machine learning, you have a much more complicated method for determining what the sulfate number should be. Is it strongly related to sulfate mass? I mean, is there a physical basis? I mean, does sulfate mass predict strongly onto the sulfate number in the machine learning algorithm?
Yes, let me see if I can move backward to the slide. So we are still looking and analyze that. So the idea is in the original, and in most of the mass-based climate model, you use the mass, use kind of simple linear regressions, get the, based on mass concentration, you get a number. So it's simple relations. But we know in the later atmosphere, the number depends on size distributions. So if you have the size informations and the size distribution change with the locations and with time, so that's will cause some of the uncertainty. Machine learning consider other variable, which it indicate the history of air mass and the other information. And we try to look into that. And this information, like trace gases and or even meteorology informations, may have implication for the size distributions. So if we have more variables, the model tends to capture more accurately the particle number and the CCN. And that's, I think, the idea. And we are still looking into that by comparing the machine learning with the really microphysics model. So I think that, yeah, additional variable will help to identify more functions, which I think is important for the aerosol cloud interactions.
Okay, yeah, so I understand that you're using machine learning to identify additional variables that are important, but I'm just wondering, I guess just the question of the physical basis for these machine learning algorithms. I mean, I was just wondering if the sulfate mass is still important, or if it actually turns out to be relatively unimportant compared to other things.
Yeah, sulfate mass definitely is important. Actually, sulfate mass is one of the most important. The mass are still important. It's actually, I think the RSU is analyzing that. If we just remove all these, use the machine learning of this to develop machine learning only based on the mass without others, they are important. But when we add that, it's improved agreement. So mass is important. And that's, I think, it's also important for the model to improve the surface mass. And I think that's good, because a lot of climate models, they have the surface mass, and the surface mass, there are a lot of measurement you can constrain and improve. So to answer your question, mass is still, and it's very important, but others can help to improve that, and especially SO2. So if you have SO2 information in there as well, so improve with agreement.
Okay, great, thanks.
Thanks.
Great, thanks. So I think that now we're past the hour. I'd like to thank you very much for giving this seminar. So we've recorded the seminar, so it's going to be available on YouTube in a few days. And so there was another comment in the chat, but it's not a question. So thank you very much for the talk, and thank you everyone for joining us today.
Okay, thank you for your time. Bye.
Thank you.
Bye-bye.
Thank you.